Everyone, and my name is Grace Peng from the Interagency Modeling and Analysis Group, and welcome to the IMAG Multiscale Modeling Integrating Machine Learning with Multiscale Modeling Pre-Meeting webinar series. And I'm happy to introduce Dr. Leonardo Angeloni from National Institute of Drug Abuse at the NIH to introduce our speakers for today.
Thank you, Grace. Good morning, and good afternoon, everybody. It's my pleasure to have today our speaker, Rusty Irving. Rusty recently retired from the GE Research, where he has led for several years the digital twin platform and was a chief engineer. He has really oversaw the development of the digital twin technology of GE, and he was the service technology leader and chief engineer where he oversaw for $50 million in service and technology projects at the company. And he has been leading, had successful engineering roles of increasing technical contribution and leadership. Rusty graduated from with a background in computer science and from Rensselaer Polytechnic Institute. And he's really look forward to going to listen to his presentation today and present all the work he has done for a span over 30 years at GE on the field of digital twin. Thank you, Rusty, for being with us. Please go ahead.
Thank you very much for the nice introduction, Leonardo, and thanks to the audience for listening in today. As Leonardo said, I recently retired from GE. And a lot of what I'm going to talk to you about in the next 15 minutes is sort of a summary of where we got to over 30-something years in doing what we really started out as, I would say, machine diagnostics. And, given that the audience here is more, in human healthcare, if you look at the title of my first slide, the subtitle, Leveraging Machine Healthcare, that's a title that has existed for us for over 10 years. And it's just coincidental with the topic at hand and how things apply to human health. Because I noticed in my journey that there was direct parallels between how we actually take care of machines. And by machines, in these pictures, you see an aircraft engine, a combined cycle gas power plant, locomotives. And, it's my conjecture that we understand and practice the medicine of machine care in some ways superior to how we actually take care of humans, and I'll at the end I'll kind of just quickly show that. So the topic here is though digital twins, which if you look in the literature really evolved over say the last 5 years. If you go back to 2010, there was only 2 references due to 2 papers. I'm going to explain, I'd say at this point almost my own personal view. Although it was the view that, we defined in GE, what is a digital twin? How is it defined? I think it's very important to understand how we got the path to digital twin, and then some actual working examples so you can see why we did it and what was the economic benefit of doing it. So, as I usually say when I give this talk, even if you only take away the first couple of slides, hopefully you understand them and you have something as a baseline to discuss digital twins with. Very simply on the left here, right, we'll have some physical asset. And again, the ones I talk about are the ones, GE was the original equipment or manufacturer for. So, and actually since these slides were made quite a while ago that I've used for years, we don't even make locomotives. We sold that business out of GE, but it was one of our very large examples. And so we sell a locomotive to a customer, and what we really do, in fact, the majority of GE's profits, over 80% over the last 15 years, was really made by servicing the equipment we sold for the customer. They're big, large, complex, expensive machines. And since we're the OEM and have all the design information and have the ability to monitor, in some cases in real time, their operation, we were actually in a position to understand, again, the health of that asset. And by understanding the health of an asset, we can help the customer get far more economic value than if you think about it, and this is one of the parallels, what we do with people. And when I ask males you know, when was the last time you went to the doctor? Most have not gone in the last year. So think about it. You get one set of discrete data points about your health once a year or less in many cases. And in the case of these assets, if we want to, sometimes we can get all the biometric markers you'd want in every minute. But here's the key thing. So what we use that data for that we collect and the environmental conditions things run in is we try to model not the entire asset because it's not necessary and it's too expensive to do so. We break things down into, I would say, system level, not so much individual parts, so we'll do that. But if you look at, if you think about what's inside a locomotive, there's a diesel engine, there is a electrical generator, and sitting underneath are electric motors that actually drive the wheels. And there's, you know, cooling systems. So we try to model at those levels to understand health. So the first big takeaway, though, to understand the concept of a digital twin is the models we build are not the digital twins. That's a very important concept. We build a model, and then when we instantiate a model against a specific asset, you see point number one, that's when a twin is born. So, for instance, if we have a specific model, I should say, you know, product of an engine, of a locomotive, and, you know, so in our case of, you know, we have one called the Evolution locomotive. The model, say, for the actual diesel engine, right, and what's going on there is not a twin. But when we instantiate it against each serial number, those are the twins. So if we have 5,000 Evolution locomotives and we instantiate that engine model and we're monitoring those 5,000, we have 5,000 digital twins. Another important thing is I'll say, reinforce several times, we have a lot of things we could model. We pick the ones that have the business outcome that can be measured. A key thing, and again, I'll always wear the GE hat. What sets our models apart, though, and I said this in an earlier conversation, they continuously learn. And what they're learning is improving. The model has to self-learn so that it constantly keeps its model error within a boundary in which the answers it produces are useful. So what happens in models, we build them, and then there's model drift, especially models that, for instance, use environmental parameters. So in the case of an aircraft engine, one of the most important things that goes on in determining how an engine is aging is the environmental conditions it flies in. So in the Middle East, for instance, we have a deteriorating atmosphere because of particulate matter there, and it gets worse every day, every month. And so you have to keep updating the weights of the parameters, for instance. If you don't do that, the model actually goes out of tolerance and it doesn't produce good answers. The other, so these 1, 2, 3, 4, 5 are the 5 parts we need to have in place for us to say, count something that's instantiated as a model. It's got to, as a twin, it's got to be based on an asset. We instantiate them against specific physical things, has an outcome. It has to continuously learn and notify when it's out of error. These actually get computationally expensive, so they have to scale. For instance, it takes a lot, just say for one engine type, and monitor 5,000 of these things. You need a lot of computer power. And also, they're very expensive to develop. On average, a team of half a dozen people might take 2 years to perfect the model that's useful. So you have to do transfer learning so that the model can be reused on another engine line. I mentioned the path. This is very important to appreciate, is if we go back to the early 80s when we started using applied artificial intelligence, really the predominant, you see, we were just trying to answer what happened. Customers would notify us the asset was broken, and we had to really just do diagnostics to figure out what happened. And things were generally rule-based, which are, I'd say, just about impossible to maintain. We had this M&D, a monitoring diagnostic center, build out so that we could figure out overall, with all the assets in a fleet, what's happening. You see the technologies listed there that started to come of age and become useful. By the turn of the century, we were very good at doing the diagnostics, and we could change the time horizon to look forward and say, what will break? So we now are moving into new customer value because we anticipate when things would break and take action beforehand. A decade later, the model fidelity got to the point where we knew how long things would last, and that gives you a whole nother power of how to schedule maintenance. And by about 2015, we realized we really had enough models of each asset that the collection of models for an asset type really constituted their digital twin. The reason we did this is, you know, for many years, GE takes in data, environmental conditions, operating parameters, and monitors over 300,000 specific assets a day. And we do this, again, for profitability. You know, the oldest business 101 equation is profit equals revenue minus cost. And we built digital twins and maintain them and run them because it helps lower cost, thereby increasing profit. And there's two ways we do that. You can, again, by being predictive in nature, you can make better decisions about what to do and what not to do, and then when to do it and how often. And that just brings more money to the bottom line. So I'll go through a couple of quick examples. In the case of an aircraft engine, very expensive asset, right? Starting price on an engine that goes on a 737 or an Airbus 320 is $10 million, right? And the customer expects to fly at a minimum of 20 years and more likely 30, and they can go as long as 40 if properly maintained. In the lower left, you see a picture there. That part is called a shroud, right? That is it's called a hot gas path part. And as I mentioned, when parts fly through the parts of the planet now that are high in particulate matter under 10 microns, they age like the one on top that doesn't look so new. And again, each dot in that graph represents a specific digital twin of an engine. And what we see as we fly them, cycles or equals flights, you get two different populations. And our ability to do this, think about the absence of doing this, we wouldn't know which planes need service sooner. And that is what, again, allows us to change the game on how we run our maintenance and service operation for customers. And again, they get greater reliability from each engine because it's more predictable what happens. And also we get more availability. And so this rather slow animation, I hope it comes through in the WebEx, shows this is what happens. We can fly a fleet of engines via their digital twins through time up to 2 years to see what fleet availability will look like. And again, that gives us the ability to work with a customer, and they can change the routes of the planes so that the engines last longer and they can manage their fleet much better. All right. We also can get more performance out of assets. So in the combined cycle power plant that's represented here, over time we've been able to understand the physics of how each specific plant, because they're all in a different geography, again, different humidity levels, altitude, all sorts of things, and advise how customers can essentially get more power out of the turbine without jeopardizing the life of the turbine parts. Because when you turn off a power plant, they on average lose $600,000 a day per turbine in lost charging for the production of electricity. Going back to the locomotive example, we built digital twin of an entire consist, in other words, the engines plus the cars, that enabled our railroad customers to get 10% lower cost in fuel, which is their top two variable costs. And I want to just close, again, being mindful of time. There's several types of twins. As I said, we can focus on parts, which is the majority of these things. We don't really do the whole product very often. The technology also works for processes. So we've applied this in supply chain. And, you know, the system twins is like the example I gave of flying a fleet forward a couple of years. And that was, you know, again, very quick treatment of how we defined it, how we built it, and, you know, that's my 15 minutes, so I'll conclude there.